Hey guys, welcome back to chapter 10. We are going to start our journey and talking about the application of intermolecular forces. One of the first things you're going to be asked to do is rank molecules based on their intermolecular force. So which one has the strongest intermolecular force, which one has the weakest intermolecular force. The only thing so far that we have to base that on is the type of intermolecular force. So something that is hydrogen bond would have the strongest intermolecular force. Something with London dispersion would be the weakest, right? But what if we have a series of molecules and a couple of them have the same intermolecular force? What if there's two of them that are dipole-dipole, right? How do we separate those two? How do we determine which one has a stronger or weaker force? So that's what today's lecture is going to talk about. So we're going to talk about three different ways to kind of delineate the strength of intermolecular forces. Again, this is sort of a hierarchy list, so I would start with polarity, and then if there's two that are kind of the same, I would go to size, and if there's two that are kind of the same, I would go to shape. So this is kind of a checklist, and this would be the order that I would check them off in. So the first one is going to be the effect of polarity. So first we know that polar molecules are going to undergo this dipole-dipole interaction, right? And this would be an additive force in addition to that London dispersion, okay? So the first is going to be polarity, right? Is it a polar molecule? That's automatically going to put it in a category above London dispersion. Okay. So let's start to look at how this might be asked in a question on a test or a quiz. So see, here we have two molecules, okay? So I might say, here is formaldehyde, and I would give you this structure, of course. Here is ethane, and I would give you this structure. Now, if I look at these two molecules, they look pretty similar in size, right? The size doesn't look terribly different. If I look at their molar masses are very, very similar, right? It's about as close as we can get. Well, how would we delineate which one of these is a stronger intermolecular force? Which one's going to have a higher attractive force? If I look at ethane, I'm going to start down here. If I look at ethane, what I see here is a lot of carbon-hydrogen bonds. So here's a carbon bound to a carbon. That's going to be nonpolar. Here's a carbon bound to a hydrogen. So you could go to your electronegativity chart. You could look at the differences in electronegativity between carbon and hydrogen. And what you would find is that is a non-polar bond or non-polar covalent bond. They're sharing those electrons evenly. If you can go ahead and commit to memory that carbon-hydrogen bonds are non-polar, that could potentially save you a lot of time in the coming weeks. So looking at ethane, I see non-polar, 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 non-polar. So there is nothing about this molecule that has any polarity to it. That's going to mean that the strongest or the only intermolecular force that it can have is the London dispersion. Let's go up here to formaldehyde, okay? Here I see carbon-hydrogen, that's non-polar. Carbon-hydrogen, that's non-polar. But what about this carbon-oxygen bond here? Yeah, if you go to your electronegativity chart, what you'll see is the carbon-oxygen bond is a polar bond. So oxygen has a higher electronegativity, carbon has a lower electronegativity. So this is a polar bond. With that being a polar bond, this is in fact a polar molecule. So we'd have a region that's electron rich up here by the oxygen, a region that's electron poor down here by the carbon. So with the introduction of a dipole moment, with the introduction of a polar molecule, now the intermolecular force that this guy feels is dipole-dipole. That is a stronger intermolecular force. So formaldehyde would have stronger intermolecular force. Ethane would have a weaker intermolecular force. That's how we delineate the two. Okay. What we're going to do in the next series of videos is we're going to apply this to properties that we see. But one of the ways that I can kind of confirm that statement that I just made is through the boiling point and melting point. So I see that formaldehyde has a much higher boiling point, so it's closer to 0. And ethane has a much lower boiling point. And that observation confirms my statement. So high boiling point, strong intermolecular force. Lower boiling point, weaker intermolecular force. And I'll explain why that is or how I know that in future discussions. Here's another example of how polarity affects the boiling point. And so you can kind of look at these series of molecules and their dipole moments. And we see that these kind of increasingly get stronger and stronger dipole moments. So not only is the fact that polarity is present, not only is that a factor, but then the difference in the electronegativity could also be a factor, right? So if the difference is 1.5 versus 2.5, that can make a difference as well. So that's the effect on polarity. That's the first thing I would look at. Is there a dipole moment? Yes or no? And if the answer is no, that's a weaker. If the answer is yes, that's stronger. So that's the first thing I would look at is polarity. The second thing I would look at would be size, okay? The larger the molecule, the stronger the intermolecular interactions will be. We've discussed this in a previous lecture, but with atoms that are bigger, the bigger the atom, the further away those electrons are, and the more susceptible to change, the more susceptible they are to outside influence. So that makes it a stronger interaction because there'll be those dipole moments happening more frequently. As opposed to a smaller atom is going to be less likely for those electron shifts to happen. And since it's smaller, less likely to happen, we won't see as many happen. So smaller is weaker, larger is stronger interactions. And that holds true for for atoms, that holds true for molecules. Now, we just said that the bigger the molecule, the stronger their interaction is going to be. Well, how do we determine if a molecule is bigger or smaller? We use molecular mass, okay? So if we're trying to compare two different molecules, we can add up the weight of all of the atoms that are present. Something with a higher molecular mass is going to be a bigger molecule. So here we see a series of organic molecules. Again, I know you're not terribly familiar with organic molecules, but the more we expose you to them, the more comfortable you're going to get. So let me talk about what these organic molecules are. So the first one down here is methane. So methane is just one single carbon atom, and that carbon atom is surrounded by 4 oxygens. Okay. The next one that we have here is something called butane. So butane is going to have a chain or a series of 4 carbons. 1, 2, 3, 4 carbons. And then surrounding those carbons, we'll have, of course, a series of hydrogens to kind of fill in the places. Then we go to hexane. Now we've got 1, 2, 3, 4, 5, 6 carbons, and then all of the hydrogens. And then we go to octane, which is 8 carbons and all of the hydrogens. So all of that to explain to you that what we're picturing here as we move up this chart is these molecules are getting bigger and bigger, okay? If I look at the chart, they're getting bigger by 1 carbon atom at a time. So 5 carbons, 6 carbons, 7 carbons, 8 carbons, 9 carbons. They're also getting bigger based on the number of hydrogens. So this one has 12, this one has 14, 16, 18, 20. If I were to look at the molecular masses of these, as we get bigger, of course, the molecular masses are going up. That's going to be how we determine the size of these molecules, is to look at their molecular masses. So as we increase the size, we increase the intermolecular attraction. Those intermolecular forces, they get stronger and stronger and stronger. And then again, that's directly connected to the boiling points as well. So stronger intermolecular forces, higher boiling points. So the first thing I would look at is polarity, right? To determine which kind of intermolecular force. If these molecules, so all of these are nonpolar molecules, all of these are London dispersion. If I'm like, man, there's a whole slew of London dispersion, how do I determine stronger or weaker? The next thing I would go to is then the molecular size. I would say, pentane is smaller, nonane is bigger, pentane is weaker, nonane is stronger. So I would rank them based on size. What if they're the same size? What if they are both nonpolar molecules? Both of them have basically the same molecular mass. We have one last thing that we can look at. And that last thing that we can look at is the shape. Okay. Here I've got 2 organic molecules. So if you look here, it's a bunch of carbons and hydrogens. Here it's still a bunch of carbons and hydrogens. So both of those are non-polar molecules. When I look at the molecular masses of these two, oh no, the molecular masses are exactly the same. So I can't rank them based on polarity. They're both London dispersion. I can't rank them based on size. They both have the same molecular mass. What can I rank them on? Now we're looking at the shape, the opportunity for intermolecular interactions to take place. So here for the N-pentane, we see that this is a long chain of carbons. They're kind of strung together in a train series here, okay? So what we'll see is a lot more opportunity for intermolecular interactions to take place, right? So bigger surface area, larger opportunity for interactions. My neopentane here is more of like a spherical shape, right? It's a much tighter shape. So when we put these two molecules next to each other, that is the smallest surface area that is possible. So spheres have the smallest surface area. So here, if I look at these two molecules next to one another, there's this teeny tiny little area for interaction to take place. So they have the same polarity, they have the same molar mass, but when I look at their shape, I would say N-pentane has a stronger intermolecular force because it's more opportunity for interactions to take place. Neopentane would have a weaker intermolecular force, less opportunities for those intermolecular attractions. Okay. So here's just another look at 3 organic molecules. Again, all 3 of these have relatively the same molar masses, We just see the connectivity is very different. So this one's a nice flat chain. We've got lots of opportunity for surface area. This one is a little bit of a chain, but the chain is shorter, and then we've got this little offshoot, so less opportunity. And then we've got this one, which is all kind of balled up together, and they are much less surface area. So here's just kind of a summary of what I would kind of check off as I'm trying to determine strength of intermolecular forces and rank them. I would first look at polarity. Is there a dipole moment? Is there a hydrogen bond? Then I would look at size. So, both of these are dipole-dipole. Which one's bigger, right? So look at the molecular mass. And then if both of those are the same, so both are dipole-dipole, both have relatively the same molar mass, then I would look at the shape of that structure. How is it all put together? Okay. So this is what you're going to use to rank molecules. You're certainly going to be asked to do this. So here is 3 molecules. Which one is the strongest intermolecular force? It's certainly something you're going to have to apply. I hope you guys found this helpful.